Welcome to my 28th tutoring session in A-level chemistry. In this video, I'll talk about types of chemical bonding. Please take a moment to watch my previous video on the topic chemical bonding, as the video will provide you with a better understanding of this video content. Link to the video is given in the description below. Please do watch the video. Don't forget to subscribe my channel, share, like, comment and watch the full video. There are two types of forces. One is the intramolecular force and the other is the intermolecular force. Let me explain these two forces with respect to hydrogen fluoride molecule. What is an intermolecular force or intermolecular bond? Now, intermolecular force are the forces that occur between molecules, and they play a significant role in determining the physical properties of substances like melting point, boiling point, solubility, and viscosity. And intermolecular forces are weak forces, or they're kind of weak bond that exists between molecules. Like in case of hydrogen fluoride molecule, as you can see, the intermolecular force is represented by a dotted line and it's a weak bond. Now here what you see is the hydrogen bond that is formed between two hydrogen fluoride molecules. So intermolecular forces are weaker than the intramolecular forces. So there are three main types of intermolecular forces. They are van der Waals forces, dipole-dipole interaction, and hydrogen bonding. And what about the intramolecular forces? Now, intramolecular forces are strong forces that holds the atoms within a molecule and are responsible for formation of chemical bonding between the atoms in the molecule. And intramolecular forces are bonds. They are stronger than the intermolecular forces, and these strong bonds exist between atoms within a molecule. And there are three main types of intermolecular forces or bonds. They are covalent bond, ionic bond, and metallic bond. So intramolecular forces or bonds, they are stronger than the intermolecular forces. So higher amount of energy is required to break this strong intramolecular force, while lesser amount of energy is required to break the intermolecular forces. So intermolecular force between the two molecules is represented by a dotted line, while intramolecular forces is represented by a solid line connecting the two atoms involved in bond formation. Now in this video, I'll give a detailed explanation about interatomic chemical bonds or intramolecular interactions. So what are we waiting for? Let's get on with it. So chemical bond is of three types: covalent bond, ionic bond, and metallic bond. Now covalent bond is formed between nonmetals. The first type is the non-polar covalent bond, and you can find this non-polar covalent bond in homoatomic molecules. That is in case of molecules with identical atoms. And in case of non-polar covalent bond, you will find equal sharing of one or more pairs of valence electrons between atoms of non-metallic elements. So here I have mentioned two examples. One is the hydrogen molecule, other is the oxygen molecule. So in case of hydrogen molecule, you can see equal sharing of one pair of electron, while in case of oxygen molecule, you can find equal sharing of two pairs of electrons. And both the elements are non-metallic in nature. And why do elements bond? The elements bond to attain the stable electronic configuration. So you'll come across non-polar covalent bond in case of homoatomic molecules, where you find the bond between identical atoms with similar electronegativity. And second type is the polar covalent bond. So in case of polar covalent bond, you will find unequal sharing of valence electrons between atoms of non-metallic elements. And again, they bond, or the elements bond, in order to attain the stable electronic configuration. For example, you will find the polar covalent bond in case of heteroatomic molecule like hydrogen chloride. And a polar covalent bond is generally represented by a crossed end, that is arrow with a crossed end. So the crossed end will be the positive end of the molecule and the arrowhead will be the negative end of the molecule. So why a dipole is created in case of a heteroatomic molecule? Because of the varying electronegativities. So generally in case of heteroatomic molecules, a bond is formed, or you'll find a bond between different atoms of different electronegativity. So here in case of hydrogen chloride molecule, the electronegative chlorine atom attracts or pulls the shared pair of electrons close to the nucleus, and therefore a dipole is created. Now this concept will be explained in detail later in the video. And third type is the coordinate covalent bond. A coordinate covalent bond is formed by shared pair of electron. So again, in case of coordinate covalent bond, you will find a mutual sharing of electrons between the atoms involved in bond formation. But a highlighting feature of coordinate covalent bond is that the shared pair of electron comes from only one atom, or the same atom, and is generally represented by an arrow pointing towards the acceptor atom and away from the donor atom. So here the donor atom is the nitrogen atom of ammonia, and the acceptor atom is the hydrogen atom of the hydrogen ion. And second type of chemical bond is the ionic bond. The ionic bond is formed by complete transfer of valence electrons from one atom to the other. So ionic bond takes place between a metal and a non-metal. So it is the metal which is losing electron, and the non-metal is gaining the electron. So ionic bond is formed by transfer of one or more valence electrons from one atom to another. So ionic bond occurs between atoms of metallic and non-metallic elements in order to attain stable electronic configuration. So I mentioned two examples here. The first example is formation of common salt sodium chloride, where you find the transfer of one valence electron from sodium atom to the chlorine atom. So here sodium is the metal, chlorine is the non-metal. So here you find the transfer of one valence electron from the metal, that is sodium, to the non-metal, that is chlorine atom, resulting in formation of common salt sodium chloride. The second example is formation of magnesium chloride salt, and here you find the transfer of two valence electrons from magnesium atom to two chlorine atoms, and that ends in the formation of the salt magnesium chloride. And the third type of chemical bond is the metallic bond, and metallic bond is formed by delocalized sharing of electrons among metal atoms. So generally speaking, so metallic bond, it takes place between metal atoms. How? By delocalized sharing of negatively charged valence electrons among the positively charged metal atoms. So what you see here is the diagram showing the sodium metal. So where you find the delocalized sharing of valence electrons among the sodium metal atom. Now, what about the intermolecular forces or bonds or interactions? So, intermolecular force are three types: van der Waals forces, hydrogen bonding, and dipole-dipole interactions. So, this will be the topic of discussion for my forthcoming video. So, please watch out for that video where I'll be explaining in detail about the intermolecular forces. So, I'll be explaining in detail about the van der Waals forces, hydrogen bonding, and dipole-dipole interactions. Now, one common and highlighting feature among the three types of covalent bond, that is polar covalent bond, non-polar covalent bond, and coordinate covalent bond, is the shared electron pair. So, shared electron pair is the common highlighting feature among these three types of covalent bond. So, in case of polar covalent bond, there is unequal sharing of this electron pair. In case of non-polar covalent bond, you will find equal sharing of this electron pair, while in case of coordinate covalent bond, you will find, though there is mutual sharing of electrons between the atoms involved in bond formation, you will find that the shared pair of electron comes from the same atom or one atom, which I'll explain later in detail. Now let me explain the polar covalent bond with respect to hydrogen chloride molecule. In the hydrogen chloride molecule, the hydrogen atom and chlorine atom is held together by a covalent bond and is shown by a solid line joining or connecting the hydrogen atom to the chlorine atom. A covalent bond is formed by mutual sharing of electron pair, but in case of hydrogen chloride molecule, the electron pair is not equally shared, but rather it is unequally shared. Now the chlorine atom, it attracts or pulls the shared pair of bonding valence electrons closer to itself, and this is shown by an arrow head pointing towards the chlorine atom. And why do you think the chlorine atom is attracting or pulling the shared pair of bonding valence electrons closer to itself? Because chlorine atom is more electronegative than the hydrogen atom. On the Linus Pauling electronegativity scale, chlorine has a electronegativity value of 3.1, while hydrogen has a electronegativity value of 2.1. So chlorine is more electronegative than hydrogen atom, and therefore it pulls the shared pair of bonding valence electrons closer to itself. And as a result, chlorine atom gains a partial negative charge, while the hydrogen atom gains a partial positive charge, which is shown by Greek symbol delta, meaning small change, that is delta plus and delta minus. That is meaning partial positive charge and partial negative charge, which is shown by Greek symbol delta. So now you have hydrogen chloride molecule with a positive end and a negative end. Hydrogen chloride molecule has a dipole with a polar covalent bond. So one can predict the polarity of a heteroatomic molecule based on the electronegativity difference between the atoms involved in bond formation. Now polarity in a polarity in a molecule with a polar covalent bond can be represented by three different ways. So one way of representing the polarity of a molecule with a polar covalent bond is by partial positive and partial negative charge on the respective atoms. So as you can see, in case of hydrogen chloride molecule, hydrogen atom is bearing a partial positive charge and a chlorine atom is bearing a partial negative charge. So this is one way of representing the polarity of a molecule molecule with a polar covalent bond. So other way of representation is by a polarized electron cloud, where you find distortion of electron density more towards the more electronegative atom. So here the electron cloud is not symmetrical, it is unsymmetrical, and therefore chlorine will be electron rich with a partial negative charge, while hydrogen will be bearing a partial positive charge, because the electron cloud is more distorted towards the more electronegative chlorine atom. And the third way of representing the polarity of a molecule with a polar covalent bond is by arrow with a crossed end. So the crossed end will be the positive end of the molecule and the arrow head will be the negative end of the molecule. So one can find the electronegativity values of the elements in the periodic table. So it is better to have a periodic table handy. To find immediate, to find the electronegativity values of the respective elements. Moving on to the non-polar covalent bond. Now, non-polar covalent bond is usually seen in homoatomic molecules. So what are homoatomic molecules? Now, homoatomic molecules are the molecules where you find bonds between identical atoms. So generally, homoatomic molecules have non-polar covalent bond, or they are non-polar in nature. Like for example, hydrogen molecule, chlorine molecule, oxygen molecule and nitrogen molecule. So all these four molecules, they are homoatomic molecules because you find the bonds between identical atoms. So in case of non-polar covalent bond, you will find equal sharing of one or more electron pairs between the atoms involved in bond formation. For example, in case of hydrogen and chlorine molecule, you will find equal sharing of one pair of electron between the identical atoms. So you find equal sharing of one pair of electron between two hydrogen atoms. In case of hydrogen molecule, you will find equal sharing of one pair of electron between two chlorine atoms in case of chlorine molecule. And in case of oxygen molecule, you will find equal sharing of two pairs of electrons between two oxygen atoms involved in bond formation. And in case of nitrogen molecule, you will find equal sharing of three pairs of electrons between two nitrogen atoms. And in case of molecules with non-polar covalent bond, the electron cloud will be symmetrical. So why the electron cloud is symmetrical in case of molecules with non-polar covalent bond? Because the bond is formed between identical atoms. So what if the atoms are identical? See, when the atoms are identical, the electronegativity difference will be 0. So for example, the electronegativity value of hydrogen is 2.1. So 2.1 in case of hydrogen molecule, when you take the difference 2.1 minus 2.1, you'll end up with 0. So generally in case of homoatomic molecules, you find the bonds between identical atoms, and therefore electronegativity value will be 0 in case of homoatomic molecules, and that results in a non-polar covalent bond. So there will be no positive end and negative end, and there will be no dipole, and that results in a non-polar covalent bond. And the electron cloud will be symmetrical in case of homoatomic molecules. And what about the coordinate covalent bond or the dative bond? Now in case of coordinate covalent bond or the dative bond, you find there is mutual sharing of electrons between the atoms involved in bond formation, but one highlighting feature is that the shared pair of electron comes from the same atom or only one atom. So let me explain the concept of coordinate covalent bond or dative bond, mentioning three examples. The first example will be protonation of ammonia molecule. Second example will be protonation of water molecule. And third example will be coordinate covalent bond formation between ammonia molecule and boron trifluoride. So let me start with the first example, that is protonation of ammonia molecule. Now in the ammonia molecule, you will find that the nitrogen atom is covalently bonded to 3 hydrogen atoms. And you will find one lone pair of non-bonding electron on the nitrogen atom. And therefore, it acts as a Lewis base. That is to say, it is an electron-rich species. While the hydrogen ion is electron deficient because it has lost its only valence electron. So you don't find any electron in case of hydrogen ion. So protonation of ammonia molecule results in formation of ammonium ion, and there is development of a formal charge within the molecule. And second example, protonation of water molecule. In the water molecule, you will find the oxygen atom is covalently bonded to 2 hydrogen atoms. And there are 2 lone pairs of non-bonding electrons on the oxygen atom. And therefore, the oxygen atom is electron rich with 2 lone pairs of non-bonding electrons, which is available for protonation. So protonation of water molecule results in formation of hydronium ion, and there is development of a formal charge within the molecule. So generally speaking, coordinate covalent bond or dative bond is exhibited by molecules having heteroatoms like nitrogen and oxygen with one or more lone pairs of non-bonding electrons. So coordinate covalent bond is exhibited by molecules having heteroatoms like nitrogen and oxygen atom with one or more lone pairs of non-bonding electrons, like in case of ammonia and oxygen, a water molecule. And coordinate covalent bond or dative bond is represented by an arrow, and the arrow is pointing towards the acceptor and it is pointing away from the donor. So what will be the donor here in case of the third example? Now third example is formation of coordinate covalent bond or dative bond between ammonia and boron trifluoride molecule. So here ammonia acts as a Lewis base, and why it is Lewis base? I've already explained, because of the presence of lone pair of non-bonding electrons on the nitrogen atom. So it is an electron-rich species and it donates the shared pair of electron, the lone pair of electron to the boron atom of boron trifluoride molecule. So ammonia molecule is acts as a Lewis base, it is a donor, while the boron trifluoride acts as a Lewis acid, it is the acceptor. So moving on to the next interesting type of bond, that is metallic bond. So a metallic bond is formed by delocalized sharing of negatively charged electrons among positively charged metal atoms. So there is a strong electrostatic force of attraction between the positively charged metal atoms and the delocalized negatively charged electrons. which gives the element its metallic nature. Now let me explain the concept of metallic bond with respect to sodium atom and magnesium atom. Now here's the electron structure or the electron diagram for sodium atom in the unreacted form or the zero oxidation state. So this is the electron structure of sodium atom in the zero oxidation state or unreacted form. The electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. Now here I have color coded the electrons. The inner core electrons are highlighted in red, while the valence electrons are highlighted in blue. And same is reflected in the electronic configuration. So electronic configuration can also be written in the shorthand form, that is 281, where 2 refers to the number of core electrons in the first shell. So here in the first shell you can find 2 electrons. And what does 8 refer to? 8 refers to the number of core electrons in the second shell, and 1 refers to the valence electron present in the outermost shell or the third shell. Now this is the symbolic representation of metal atom without the valence electron. So a red circle with a positive charge is a symbolic representation of metal atom without valence electron. And this is a symbolic representation of valence electron, that is blue circle with a negative charge. So a red circle with a positive charge and a blue circle with a negative charge is the symbolic representation of one metal atom. Only one metal atom. So this is about the electronic configuration and the electron structure of sodium atom. Now what about the physical state or the physical appearance of a sodium metal? Now sodium metal is a soft silvery white solid metal that can be cut with a knife. Now the sodium metal is so soft that it can be cut with a knife. And the density of sodium is 0.97 grams per centimeter cube. That is to say, it is less dense than water, and therefore sodium metal tends to float on water because it's less dense than water. Now let's take a closer look at the metallic structure of sodium metal. So when you observe the metallic structure of sodium metal very closely, you will find delocalized sharing of negatively charged valence electrons among positively charged metal atoms. So the valence electrons are loosely held and are free to move. And these loosely held and freely moving valence electrons gives the metal its characteristic properties like good electrical conductivity, good thermal conductivity, malleability, that is the metal can be hammered into sheets, ductility, metal can be drawn into wire. So sodium metal can also be drawn into thin wires. And it also gives metallic luster. So what is metallic luster? So metals generally, they tend to reflect light and therefore they shine or glitter. So that is called metallic luster. And the strong electrostatic force of attraction between the delocalized negatively charged electrons and the positively charged metal atoms is what gives the metal its characteristic high melting and boiling point. So for example, a steel, copper, gold, aluminium, silver, so many examples. So they have high melting point. And this is the reason. Strong electrostatic force of attraction between the positively charged metal atoms and the negatively charged delocalized freely moving loosely held valence electrons. A second example is the magnesium atom. Electronic configuration of magnesium is 1s2, 2s2, 2p6, 3s2. Remember, the core electrons are highlighted in red while the valence electrons are highlighted in blue, and the same is reflected in the electronic configuration. The shorthand notation, the electronic configuration of magnesium is 282, where 2 refers to the number of core electrons in the first shell, 8 refers to the number of core electrons in the second shell, and 2 refers to the number of valence electrons in the outermost valence shell. And this is the unreacted form of magnesium, or zero oxidation state. And talking about and this is a symbolic representation of magnesium in the zero oxidation state, where the red circle refers to the positively charged metal atom without the valence electrons, and the 2 blue circles refer to the negatively charged valence electrons. So the only difference between, so there are two differences between the electron structure of sodium and magnesium. Sodium, there are 11 protons in the nucleus. Magnesium has 12 protons in the nucleus. Sodium has only one valence electron, while the magnesium has 2 valence electrons in its outermost shell. So these are the two major differences between the electron structures of sodium and magnesium. And talking about the physical appearance of magnesium, or the physical state. Now, magnesium is a shiny gray solid metal, and it is commercially available as a thin ribbon. And when you take a closer look at the metallic structure of magnesium, you will find delocalized sharing of negatively charged, loosely held, freely moving valence electrons and the positively charged metal atoms. So the same explanation holds good even in case of magnesium. So only difference is the number of valence electrons. So number of valence electrons in case of magnesium is 2, and in case of sodium it is 1. So here you can find the size of the metal atom is smaller in case of magnesium as compared to that of sodium atom. That is because magnesium, so when you compare and contrast the nucleus of sodium and magnesium, you will find that sodium has 11 protons while magnesium has 12 protons. So the number of protons is more in case of magnesium, and therefore the effective nuclear charge is more. That is, electrostatic force of attraction between the nuclear protons and the outermost valence electron in case of magnesium will be more. And that leads to, and therefore the size will shrink, and this leads to close packing of the metal atoms. So close packing of metal atoms, small size of metal atom leads to close packing, and close packing of metal atom leads to stronger metallic bond. So metallic bond is strong in case of magnesium as compared to sodium. So metallic bond occurs between metal atoms in a solid metal. That is, for example, sodium and magnesium metal, which I just explained. And you find a delocalized sharing of electrons among metal atoms. And in metal bonding, the valence electrons of the metal atoms are loosely held and can move freely throughout the entire crystal lattice. And this creates a sea of delocalized electrons surrounding the positively charged metal ions. And what is the role of the delocalized electrons? Now here, the delocalized electrons are not associated with any specific metal atom, but rather it is shared by all the atoms in the crystal lattice. And this gives metals their characteristic properties, which I just explained, such as high electrical and thermal conductivity, malleability, ductility, and metallic luster, and high melting point and boiling point. So as the number of valence electrons increases, there is a corresponding increase in the packing of molecules, metal atoms, and that results in increase in melting and boiling points. And what are the factors governing the strength of metallic bond? Now, strength of metallic bond depends on several factors, like the charge of metal atoms. So charge here, it is referring to the nuclear protons. So there are 11 protons in case of sodium, 12 protons in case of magnesium, and 13 for aluminium. So more the charge, stronger will be the bond. So more the number of protons. So here charge is referring to the number of protons. So more the number of protons, stronger will be the Coulombic force of attraction between the positively charged protons and the negatively charged electrons. And that leads to increase in strength of the metallic bond. And what about the size of metal ions, that is talking about cations. The size of aluminum ion is less than that of magnesium, and magnesium in turn is less than, the size of magnesium is in turn less than that of sodium. So as the number of nuclear charge increases, the size of the metal ion or cation decreases, and with decrease in size of the metal ion or cation, there is close packing, and with the increase in close packing, there is the strength of the bond increases, and with the increase in the strength of the metallic bond, it leads to high melting and boiling point. So this is about the metallic bond. Now moving on to the last type of bond, that is ionic bond. So ionic bond is formed by complete transfer of valence electrons from one atom to another atom. That is, there is transfer of valence electrons from metal to a non-metal. So it is the metal which is losing electrons, and it is the non-metal which is gaining the electrons, resulting in formation of oppositely charged ions. And it is the strong electrostatic force of attraction between these oppositely charged ions that gives the strength to the ionic compound, or strength to the ionic bond. So stronger the electrostatic force of attraction, stronger will be the bond. So let me explain the concept of ionic bonding with respect to sodium and chlorine atom. Now this is the electron structure of sodium in the unreacted or the unreacted form, or the zero oxidation state, and this is the electron structure of chlorine atom, that is in the zero oxidation state. So in the zero oxidation state of sodium, that is in the unreacted form, you will find a total of 11 protons in the nucleus, 2 electrons in the first shell, 8 electrons in the second shell, and only 1 valence electron is in the outermost shell. Well, in case of chlorine, you'll find a total of 7 protons in the nucleus of chlorine atom, 2 core electrons in the first shell, 8 electrons in the second shell, and a total of 7 valence electrons in the outermost valence shell. So sodium being a metal, it loses the outermost valence electron to the chlorine atom, and chlorine being a non-metal, it accepts the electron given by the sodium metal, that is sodium atom, and this results in formation of sodium ion and chloride ion, that is the common salt is formed. Now I said sodium is a metal, therefore it loses electrons. Chlorine is a non-metal, it gains electrons. Fine. Now what is the driving force for the sodium metal to lose the electron? There should be some reason. So there are two reasons. The first reason is the sodium atom has a low ionization energy, and therefore it tends to lose electron. And second important reason is that it loses its only valence electron in order to attain the stable electronic configuration, that of the nearest noble gas, that is neon. So electronic configuration of sodium before losing electron is 281, and after losing the outermost valence electron to the chlorine atom, it attains the stable electronic configuration of neon, which is the nearest noble gas in the periodic table. And what about chlorine atom? Now chlorine atom electronic configuration is 287 before accepting the electron. After accepting the electron given by the sodium atom, it attains the stable electronic configuration of argon, which is the nearest noble gas in the periodic table, and that leads to formation of the common salt sodium chloride by the oxidation of sodium and reduction of chlorine atom. So sodium, after losing the electron, it has attained a oxidation state of +1. It has attained a positive oxidation state of +1. And what about the chlorine atom? Chlorine atom, after gaining electron, it has attained the negative oxidation state of -1. So sodium has lost 1 electron and chlorine has gained 1 electron, and therefore sodium has positive oxidation state of +1, while chlorine, after gaining electron, it has attained a, or it has taken a negative oxidation state of -1. So ionic bond basically is formed by complete transfer of valence electrons from one atom to another atom. So metals lose electrons and non-metals gain electrons. So here in this particular example, what I've explained, you can see the transfer of electrons from sodium atom to chlorine atom, resulting in formation of common salt, that is sodium chloride. So the strong electrostatic force of attraction between the sodium ion and the chloride ion holds the ions together in the crystal lattice of the common salt. I'll also give you the diagram of the crystal lattice. Now sodium ion is smaller as compared to the chloride ion. Why is that? Because the sodium ion, it has lost its only valence electron, and in the process it has lost its outermost shell, while the chlorine on the other side is bigger because it has gained an electron from sodium, and after accepting the electron it leads to inter-electronic repulsion, and that leads to expansion of the electron cloud, and as a result the chlorine atom, the size of the chlorine atom increases, and the end result is that both sodium and chlorine, they have complete stable octet electronic configuration. So the sodium and chloride ions in the crystal lattice are held together by strong ionic bonds formed through the attraction, Coulombic force of attraction, Coulombic force between the opposite charges of the ions, and therefore the melting point of sodium chloride is around 801 degrees Celsius. So you can just imagine the strength of this ionic bond. So by the melting point of sodium chloride, you can just imagine the strength of the ionic bond. So a very strong bond. So the basic unit of sodium chloride crystal structure is called the unit cell. And the unit cell represents the smallest repeating unit that when stacked together forms the entire crystal structure. So in the case of sodium chloride, the unit cell is in the shape of a cube, as you can see in the diagram. And the face-centered cubic arrangement of sodium chloride results in a high degree of symmetry. Now you can see in the diagram, the ions are arranged in a manner that creates a repeating pattern, with each ion having the same environment of surrounding ions. So this regular and symmetric arrangement gives sodium chloride its characteristic crystal shape and properties. So what I have shown here in this diagram is only one unit, which you see in the shape of a cube. So this unit cell, what you see, represents the smallest repeating unit. So this unit, when stacked together, there are several units stacked together, leads to formation of the entire crystal structure. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in the next interesting tutoring session.